there's some graphing, and among the things that you might have forgotten about in this chapter, we had to graph lines. And so I think you've graphed this line enough times to where you should know mx plus b. And so in this case, we're going to start at 6, 1, 2, 3, 4, 5, 6. And then this is a slope down 2 and over 1, down 2 and over 1. You know the drill. You've done this a million times. Okay, there's no reason that you shouldn't be able to graph a line. Now, the second one is in standard form. And so if you wanted to change that to mx plus b form, you could. But I showed you in class what I think is a better way of doing it. I'm going to make a table and plug in 0 for x. And if you plug in 0 for x, that kind of falls out, and you're left with a simple equation that you can solve in your head. 4y equals negative 24. Well, in order for that to be true, y would have to equal negative 6. So I've got a point, 1, 2, 3, 4, 5, 6. I've got this point right here, 0, negative 6. Now, the next thing I'm going to do is I'm going to plug in 0 for y, and that makes this part kind of fall out. So I've got another simple equation, negative 3x equals negative 24. Well, that means x must equal 8. So I've got the point 8, 0 right there. 2 points is good enough for a line. There you go. I like that method. If you want to change it to mx plus b, be my guest, but I think that's probably more efficient. Piecewise functions. I know students kind of struggle with piecewise functions, but split it up. This first piece is kind of like you're graphing y equals x. And if I was graphing y equals x, you can think about it as 1x plus 0. You'd start at 0 and go up 1 over 1, up 1 over 1, up 1 over 1, like that. And so the line looks something like this, sort of. What you have to consider, and a lot of people don't, but you have to consider that this says I only want to look at that line when x is less than 1. So think about the domain. The domain of x less than 1 would be right here. I only want to look at that line when x is less than 1. And so I need to get rid of that part on the right. And normally I would go all the way up to this point right there. However, since it says not equals, I'm going to leave an open circle right there just to show for sure that we are not equal at that point. Open circle. Now, you've also got this equation, which is y equals 2. And y equals 2 is a horizontal line. Looks like that. That's y equals 2. But what you must consider is they only want that equation when x is greater than or equal 1. So we don't want any of that. We only want it from 1 and more. And then since it says equals, I would probably put a filled in circle right there. Now a reminder, when you see a graph that looks like this on Math Excel or on your graph paper or whatever, sometimes it doesn't have the arrows on the end of it. But if it runs out of room, you should probably assume that that means that there's an arrow and it goes on forever and ever. That's a piecewise function. If I had to evaluate, if I had to say something like f of 4, you go 1, 2, 3, 4. That's this value right here. That's 2. Or you say, well, this is my x number. My x number, when x is greater than 1, I'm at this value. Whereas if I said f of 0, and my x number is 0, you'd have to say, well, that x number is less than 1, so I look at this piece. So f of 0, plug in 0, you get 0 right there. Or look at the graph right there. F of 0 is 0. Graph the parabola. Well, maybe I shouldn't have told you that was a parabola, but you should recognize this is a parabola when you see that this has an x squared in it. This has x squared, so you should know that's a parabola, and you should remember the 1, 3, 5 pattern. But other than that, you should recognize that this is a flip, and so my parabola is upside down. And this means left 3, and this means down 7. We've got these transformations on that parabola. So I would think about going left 3 and down 7. Left 3 and 1, 2, 3, 4, 5, 6, 7. Left 3 and down 7. It's a flipped parabola, meaning I'm going to use my 1, 3, 5 pattern, but I'm going to go down. Go down 1 and then down 3 would put me like right there. I'm kind of out of room, but that's my parabola. It's a flipped parabola that's shifted left 3, down 7. Find a linear model, the R-squared value, and predict the value when x equals 100. This is like what you're going to need a graphing calculator for. Either you've got a graphing calculator or you've got a website. So I'm going to go sit down to type that in. I think it'll be easier. Let's see. Wait on regression. Okay. So if you have to draw a scatter plot, I don't know if I would copy this. It would almost be easier just to take your numbers and draw your scatter plot. But you look through all these numbers, and here's your R-squared number, and at the bottom, that's your equation. Your linear model is your equation. So I'm just going to copy and paste this. Yeah. Find the linear model, that's this. Find the R-squared value, that's this, and predict the value when x equals 100. So all that means is you're going to plug in that value into your equation. So okay, I've got 0.4537 times 100 plus 50.98, 96.35, 96.35. So make sure you know how to use that calculator or whatever's on your calculator. Find and graph the point if there exists x-axis, y-axis, and origin symmetry. So another thing that seems kind of minor that we didn't talk about a whole lot, but it's going to be on there. So make sure you're in tune and ready for this. When you talk about x-axis symmetry, you switch the y-coordinate. And if you talk about y-axis symmetry, you switch the x-coordinate. And when you talk about origin symmetry, you switch them both. So you need to kind of remember that. X-axis, you switch y. Y-axis, you switch x. Origin, you switch both. I think it's a lot easier if you just think about the graph. If I've got -3, 2, and that's graphed right there, -3, 2, and we had to do x-axis symmetry, well, that's just going to be right here. The x-coordinate stays the same, but we flipped the y-coordinate. And if I look at y-axis symmetry, then I flip it over the y-axis, and the x-coordinate changed, but the y-coordinate stayed the same. If I do origin symmetry, I flip them both. That's going to be down here, so use your common sense. I changed them both. Perform the function operations. Okay, so now we're getting into stuff that's more recent. In this first problem, it says add, and I think it's easier to understand if I said this. f of 4 plus g of 4. That's what that means, but you're definitely plugging in 4. If you plug in 4 into the f function, that's going to be 4 times 5 is 20, plus 2 is 22. Plus, if I plug in 4 into this one, that's 12, plus 9 is 21. That's 43. All right, I'm just going to check that. That's 22. That's 21, 43. Okay, so now if I subtract, I'm going to do f minus g of 3. So put a 3 in here. That's 15. That's 17. Minus, put a 3 in here. That's 9 plus 9 is 18. 17 minus 18 is negative 1. This next one says multiply f of 2. So if I plug in a 2, that's 10 plus 2 is 12. Times, if I plug in 2 right there, that's 6 plus 9 is 15. 12 times 15. Not confident about that one. 180. Next one says divide if you plug in negative 1. So if I plugged in negative 1, that's 5 times negative 1 is negative 5, plus 2 is negative 3, divided by g of negative 1. That's going to be 3 times negative 1 is negative 3, plus 9 is 6. You get negative 3, 6. That reduces to negative 1/2. Okay. Then composition f of g of negative 2. F of g of negative 2. Students kind of struggled with this. I think it makes more sense to think of it this way. Composition of functions means that you plug a function into a function. So what I'm going to do is I kind of work backwards. I take a negative 2 into the g. So if I plug negative 2 into the g, that's negative 6 plus 9 is 3. And so negative 6 plus 9 is 3. What I've done is found g of negative 2. G of negative 2 is 3. But now I have 3. I don't have negative 2 anymore. It's done. I've got 3. And I'm going to plug 3 into the f function. So I plug 3 into the f function. That's 15 plus 2 is 17. Now I've got the same exact question, except this time we leave the x in there. Instead of plugging in a number, you plug in x. Well, if I'm going to plug in x, I just get this. That's exactly what I get right there. I'm going to take this one plus this one. So 5x plus 3x is 8x, and 2 plus 9 is 11. Next problem says subtract them. So we're going to subtract 5x minus 3x is 2x, and 2 minus 9 is negative 7. Be very careful. If either of these two is negative over here, you're subtracting negatives. It's really easy to trip over a negative. Next one is multiplication. This is one I was kind of surprised at the number of people that messed this up a week or so ago. But if you multiply them, we've done this a bunch of times, or you have. You got to distribute. You're going to get 15x squared plus 5x times 9. That's 45x. And then you distribute over here. 2 times 3x is 6x. 2 times 9 is 18. Like terms here, that's 51. 15x squared plus 51x plus 18. Next problem says divide. F divided by g of x. This one's easy because all you have to do is say this is f of x and this is g of x. And I suppose sometimes you might have to reduce it, but not in this case, you don't. So that's it. Now your composition, f of g of x. Let's go over here again. F of g of x. It's like f of g of x. And what that says is, think about it backwards. You plug x into the g function, and this is exactly what you get, 3x plus 9. But what you're doing is you're taking the 3x plus 9 and plugging it into the f function. So that goes right here. There won't be an x anymore. There won't be this x anymore. That's an open space. F is the function that says 5 times something plus 2. A lot of times when it's a number, you can do it in your head, but I don't know if I would recommend that in this case. You're plugging one function into the other function and then just clean it up. Distributive property, that's 15x plus 45, plus this 2 over here, that's 47. 15x plus 47. Find the inverse if possible. So again, that if possible means that sometimes it won't be possible. This 1 is going to 6. This 2 is going to this 4. There aren't any doubles. Nothing gets doubled up, the x or the y. It is a function. It is one-to-one. There is an inverse. And so for an inverse, all you do is switch x and y. Four goes to the 2. 6 goes to the 1. Look like that. Next one, is that invertible, I guess. So one thing to do to determine if it's possible is think about what that looks like. Well, 2/3 x plus 5/3. That's a complicated looking line, but that is a line. That is a line, and a line is a function, and a line is also one-to-one, so that means it does have an inverse. So how we found an inverse. This is a good review of 1.7, by the way. This is probably the most important problem of 1.7. The steps for finding an inverse are change this to a y, then switch x and y, then isolate the y. So if I want to isolate the y, I'm undoing the operations. And so that's kind of what an inverse is. Two inverse functions cancel each other out. They cancel out all the operations. So I would multiply by 3 to cancel that fraction. 3x equals 2y plus 5. I'm trying to iso the variable, so let's subtract 5. 3x minus 5 equals 2y. Divide by 2. And you're looking at 3x minus 5 over 2. That's your inverse. And so the last thing we do is just kind of replace the y, go back to our function notation. F inverse of x equals 3x minus 5 over 2. I know there is a problem on Math Excel that's going to make you graph that. If you had to graph it, I might split it and say 3/2 x minus 5/2. That might be easier for you, and that's also correct.